I'm going to begin this talk with some motivation from XKCD that came out a couple weeks before I needed my talk. It was very convenient of him to do that for me. It says that installing things has become so fast and painless, why don't we skip it entirely? We can make a phone that has every app installed already, and we can just download and run them on the fly. And I felt pretty clever until I realized I invented web pages. Now, where's the intuition for this cartoon come from, right? Why is installing fast and painless? I mean, it wasn't always that way, right? Desktop computers in prior decades, installing was very painful because it entails a lot of risk, right? There's some chance that you might install a vulnerable or a malicious program, and then everything else about your computer is now broken. But that's not the way it works on the web, because on the web, the websites that you use are autonomous. So they're logically separate. So whether or not you visit Flickr's web server doesn't have any effect at all on your Amazon account. Or if it does have some effect, it's because Amazon and Flickr have negotiated to do some sort of SOAP interaction behind the scenes. But it's not going to. The point is these sites run autonomously. So if Flickr's servers today turn out to be vulnerable to Heartbleed, well, that's not your problem as a user, right? Flickr needs to identify the problem and correct the vulnerability, but they do that on their servers, and users don't even think about that. This works because Flickr controls the entire stack of software that's running on their servers, and they accept the responsibility to patch and maintain that server software. Now, the cartoon was funny, but it's not actually entirely true that we have the same property on clients. When we send an application down to clients today on the web, we send a couple hundred kilobytes of JavaScript, but sitting underneath that is some software that the user is responsible for, maybe a browser and some graphics stack and an operating system. And the same is true on mobile operating systems as well. You might send an application, but underneath that is hundreds of megabytes of libraries and operating environment that support those mobile applications. So last year at NSDI, we presented a paper called Embassies. And the idea here was to extend this notion of autonomy from servers onto the client. So the idea was that every vendor out in the cloud, when they would send content to the client, rather than sending a thin stack of software that runs on top of the browser, they would send an entire stack of software, all the way down as low as we could go to nearly the hardware, that runs in an isolated container. And so these would all end up on the client. And if they want to communicate, there's no infrastructure that's common in the browser for that. All the communication is exclusively via IP, so that we have the same notion of autonomy among the applications. So the idea here is that now there's nothing left for the user to break, right? Because there's no common software underneath that can become vulnerable, because there's very little left. So this intuition has a lot of benefits for end users. For it to work right depends on very strongly getting right this notion of minimality. That all there is on the client is some very simple stuff that all the applications can trust, because this is really what the trusted computing base is. So what runs on the client? Well, we have this notion of a pico process, where you get to send some native code, and it can allocate some memory, it gets a single address space, and it can get some threads and be able to do some scheduling. And once you have that container for native code, you can send everything else you need. So as I mentioned, all the communications are via IP. If you want TCP, if you're a vendor and you want to send an application, that application is going to speak HTTP, and that needs TCP. You send all that stuff, the HTTP stack and the TCP stack, goes inside your container. Now, IP is sort of a hard world to live in, so if you want integrity and privacy, you're going to need some crypto. So our Pico process kernel provides a few primitives for that. And then the whole point of sending this code to the client was to get close to the user and have good interactivity. So we need some way to get pixels on the screen and do graphics. But we don't want to put buttons and graphics and things all inside the trusted computing base. All that stuff should be libraries that the vendors send. And so all they do is they paint off-screen bitmaps when we put those on the screen. So this was the idea behind Embassies, was to make most of all the work that's happening on the client happen inside the applications. And this is all that's there. But you notice what's missing. There's a bunch of stuff missing. There's no file system. There's no common buffer cache. There's no fork. There's no exec. How do we get applications started? In this world where we're making the client really, really minimal, there are two important consequences, and they work together to make our life kind of tough if we want to do this. The first one is that now the applications are really big. Instead of 100 kilobytes of JavaScript, we're shipping down 100 megabytes of JavaScript and HTML, and then whatever the rest of the rendering stack is that supports that. And then, in addition to the fact that we now have to move around these really big applications, we no longer have that trusted buffer cache as part of the in file system to support starting those applications quickly. So when we would sort of ship this idea around for Embassies, one of the first reactions that we often got was, that's crazy talk, you're never going to actually be able to start applications quickly in this world. What if I told you that in this environment, we could start these big, huge applications not only quickly, but on the time scale of hundreds of milliseconds? So that's the premise of this talk, that we can achieve this hopefully sort of surprising result. So there are two things we're going to need to make it happen. The first one is we need to have the right assumptions about commonality. The question is, I mean, if this is going to work, I mean, if we're going to have something that acts the way a trusted buffer cache works, it works because we're exploiting caching and we have commonality available. So I'm going to make an argument that commonality will be available in this world. And then we also need to argue that we can exploit it, that we have that if we put the right technical pieces together, we will be able to see this actual performance improvement. So the first half of the talk then, first half of the argument, is that these 100 megabyte applications will in fact expose commonality. So the intuition again comes back from this analogy. What happens when you go to these web servers, right? The web servers could run anything they want, right? This argument about autonomy is that Flickr chooses its software stack and Amazon chooses its stack and Facebook chooses its stack. And those things could be entirely different. But in practice, even though there are millions of websites in the world, there are a few common pieces that they use because they don't want to redevelop everything from the ground up. So that intuition, if they need an SMTP server, maybe they can use Postfix or Qmail or Exim. So we're going to argue that same intuition should apply in the client world, that even though it's important that vendors can choose any software they want, that in practice they'll commonly use standard components. So to support this, we did a study, and we found sort of a bunch of best of lists and collected 100 sort of top interactive desktop applications, because that's the kind of stuff we want to run when we put it on the client. So this is a huge variety of things, spanning the gamut from vector illustration, a web stack, since that's where we're trying to show that we can do anything we can do there, but music composition, software development, chemical analysis. It's in languages from C and C++ to Java, Python, Perl. So there's a huge variety of applications here. But when we go and we look at these applications, we find that there is actually plenty of commonality to exploit. So this picture here is looking at these applications' install sizes, and the line on the right that I've chosen in high contrast yellow is the CDF for the size of these applications. And it shows that the median size of these applications is around 200 megabytes in this sample set. But the important feature here is that these applications have a lot in common. If we say put 6 of these applications into the cache, then installing the 7th one, the median amount of data we have to get is much smaller, on the order of 40 megabytes or so. And as the cache gets bigger, we kind of get toward this asymptote, well, what's looking like an asymptote. We only had 100 apps in our sample, of only needing to install something like 10 or 12 megabytes. So there's definitely commonality here, something like an order of magnitude. But the story gets better, because what we're interested in here is fast start. You're going on one site, you see a cool link, and you click on it, and you go to a new site, and they need to send you their content, and we want that to become interactive as quickly as possible. So we don't actually care about installing the whole app. We care about the part of the app you need to make the application become interactive quickly. So we call this the startup set. And when we take these same applications and look at their startup sets, well, we get an improvement right away. Now the median size is only 64 megabytes for a single app. So this is a factor of 3. But more importantly, there's even more commonality among the initial parts of the application. That if we look at commonality, now these things get down into the megabyte range of the amount of data that's actually different among the applications. And then we can stream the rest of it in the background. So there's a lot of flaws with this study, and you can argue about them with me in the hallway afterward. But the takeaway message is that there are a couple of orders of magnitude of commonality that are likely to be available. And if we can exploit them, we can get these startup times to be really fast. So that brings us to the second question: is how can we exploit that commonality without a trusted buffer cache? So the argument here is that we need to be able to exploit the commonality to save on network bandwidth, because nobody wants to wait around for 100 megabytes to trickle over the network. And we also need to worry about the local case, right? Even you've been to the site before, but we need to load it quickly out of the cache so we can start it up again. So to describe to you why this problem is hard, let me go into a little more detail. I said earlier we don't have fork and exec. Well, what does it look like to start an application in a world with this minimal environment where you don't have fork and exec? So I'm going to walk you through this diagram. In this picture, the bottom thing is that little microkernel shaped thing on the client that doesn't do very much for us at all. All the work is going to happen up in the applications, these mutually distrusting components. So the thing on the left is an app that's already running. We'll call it A. And this is where the user is clicking to start another app. The middle box is going to be the application we're trying to start, but we haven't started it yet, so let me not highlight it. And then the app on the right is some caching application. Nobody trusts it, but it's going to help out because it's where we're going to collect the common blocks to make applications start work quickly. So the way this works is that the user is just sitting in application A, and they click on a link, and the link says, well, I want to go to B. And so that application uses some mechanism, that's up to the app. It's not part of the client-side definition. Say DNSSEC or something to resolve the string B into a definition of the application they want to start. And so what they get back from this process is a boot block, which is a little, say, kilobyte of executable code, of native code, and a signature on that that says this is what B wants to do. So it takes that boot block and it calls the kernel with the instantiate call. And the only thing the kernel does with it is it checks the signature and says, yep, that's really B's boot block. This thing represents B's intentions. So it creates a process, labels it B, and says whatever happens in here, it's B's problem because B signed it. And then it makes a thread and jumps into that process. So now it's the process's problem. That little boot block now has the challenge of turning itself into this 100 megabyte process. So what it does is it says, oh, well, I have a signature here, and one of the things that's signed is the hash of the image that I want. And I will just punt that over to another process, say on the same machine, that's going to go collect that boot block. And so that the cache process now, the one we don't trust, will look up that hash and say, oh, here's a recipe for the content we need. Oh, look, a whole bunch of that I already have cached because it's common with other applications. The rest of it we can get any way we want. We can use hints that were provided by the boot block. We can go to an origin server. We can get it from nearby machines in a peer-to-peer network. It doesn't matter how we get them. In the end, we'll assemble that 100 megabyte image. And now we have to get it back over into the first application. I told you all the communication is IP. We don't have magical kernel to move around the buffer cache. So that's fine. We'll just use an IPv6 jumbo frame and send a single 100 megabyte packet, which turns out to move quickly in this world because we can actually use down in the kernel, even though we're getting the nice clean semantics of IP, it's fine to do that with a memory remapping. So now we're getting the nice clean semantics, but we're moving the data very quickly. Now I've got 100 megabytes in the application, but we don't trust it because it might be the wrong 100 megabytes. So the last step is for the application's boot block to check the hash and make sure it's safe to start it. So this is this is the sort of hostile environment we're living in. We're trying to survive without much trust in the kernel. Now where does that application image come from? The model we have is that a developer maybe, say they want to build on a HTML-like stack, a web-like stack. They write some HTML and some JavaScript like they would today. But in their integrated development environment, when they click F5, rather than just shipping that directly to the client, that gets linked together. It's sort of the equivalent of linking an application into what we call a ZAR file. That's meant to sort of be an appeal to like a tar file. And a ZAR file is a big bag of all the files, all the executables and libraries and PNG files and whatever that make up this application. An important feature of a ZAR file is that it has this Merkle Tree recipe that describes it. And the reason we need that is for two things. When we get to the client-side cache, it wants to, one, only download a subset of that image, right? Remember, we only want to get the startup blocks, the things we actually need to make the application start right away. And having a Merkle tree means we can check that we've got the right blocks. The other thing we want to do is we want to exploit commonality. So having the Merkle tree lets us say, oh, this block, I don't have to go get it because I've already got it in my cache. So that's kind of the way an image gets to that application. Looking inside the ZAR file, this is a pretty conventional Merkle tree structure. We have some data blocks at the bottom and a Merkle tree, and then we smoosh in some metadata at the top. The argument here is not that we invented Merkle trees. The argument is that these are sufficient to achieve the surprising result that we can get the good performance. So some of the questions we want to ask to squeeze out every last bit of performance is, for example, what's at the bottom of the tree? Are those variable length strings or fixed length blocks? Well, if we want to start applications fast in the hot case, having fixed length blocks is nice because that way we can just use memory remapping operations to reassign blocks into images. So we went with blocks. But once you have blocks, then you have interesting questions like, well, how big should the blocks be? If they're small, you have these, too much metadata in the recipes, and if they're big, then you waste too much space in the padding at the end of the blocks. Which led us to this observation that we could pack small files in a clever way. So if we do the basic thing, we have a bunch of files we want to cram into this image. So let's say we lay out the elephant files, and they waste a little bit of space. And then we go through laying out all the little mice files at the end, and they waste a whole bunch of space. So this is, the space isn't a big problem because it'll compress nicely, except that it's bad for the hot case because now we've got more sort of per byte operations cost more. For example, we want to hash this thing. But I used elephant and mice to make you sort of trigger your pattern matcher for heavy-tailed distributions. So these ZAR files in our experience have the same distribution, in our measurement of that data set, have the same distribution that any heavy-tailed thing does, where almost all of the files are small. Almost all the files are mice, but almost all the bytes are in the elephant files. So that means what we can do is we can lay the elephant files out like we had before, and then we can just pour the little mice files into the gaps at the end of the elephant files. So there's a little cost to that, right? We're losing commonality opportunities at those padding boundaries where the mice are sort of making uniquely shaped blocks, and the last block of every elephant is going to be uniquely shaped. But it doesn't cost very much because there aren't that many mice files. Almost all the bytes aren't that many mice bytes. Almost all the files are in the bytes are in the elephant files. There's a couple other things in the paper details about sort of tuning this up to get the good performance, but I will let you look those up in the paper. The last little bit is when we get that image into the application, we have to verify it. Just doing a hash, this per byte operation, is still pretty expensive. On our hardware, it was about 400 CPU milliseconds to hash 100 megabytes. So one of the things that we do is we use what's called a VMAC, which is like a hash, but it depends on having a secret available. So the first time we launch your application, we have to do the public hash. But then we take a VMAC using a secret that's provided by the kernel. That's some of that cryptographic support I was talking about. And that lets us shave an order of magnitude off of the time it takes to verify that we have the right bytes in the hot case. So all of those techniques, each of those pieces is familiar, but when we put them together, we get this sort of surprising result. That in this world where the kernel is doing almost nothing for us, we trust very little about it in the kernel, we can get very fast launch times. So in this picture, we're looking at a few different applications. And most of these applications, since Embassies is trying to make this argument, we can sort of drag the web world over here. Most of these are based on WebKit, but it generalizes. We've got GIMP over there on the right. The first column in each of these is showing a WebKit application and a corresponding site loading up on a conventional Linux box. And what you'll see is in the next column over, if you compare them, the next column, the middle column, is how long it takes us to start that application in the hot case, where all the bytes are in the cache, and we already have that VMAC optimization available. And you'll see that it's never more than about 100 milliseconds additional cost. Now, there's also the warm case, where we actually have to go get some content, and we have to do this more expensive operation of reassembling the bigger image and doing the more expensive hash. But even then, we're still within a few hundred milliseconds of the right amount of time. And one of the important observations, you might think, well, 100 milliseconds sounds pretty bad for a page load. But this isn't a page load. This is changing sites, right? Within a site, that site can go as fast as it wants. They can send you an optimized browser that's better than whatever browser you were using last week. So I think the argument here is that we really can get this kind of performance. If we want to have these highly isolated clients, the opportunities will be there. Client applications really exhibit commonality. The untrusted cache, we really can get the cost down into 100 milliseconds. So this crazy idea of launching these 100 megabyte applications on the fly, it's actually feasible. That's all I have. You believe me? Okay, good. All right. Go ahead. Yeah, that's a good question, and you might even back up a step further and ask, were the commonality results we showed, they didn't even reflect that possibility as versions differ, and I don't really know the answer whether that would still make sense. I think what we wanted to show is that it was plausible that we could get good performance, and one of the nice things about this architecture is that if you want to shift to a different mechanism, if you want to start using a different caching system, any vendor can choose to do that at any time. They're just going to pay some performance cost to do it. So I think what we needed was an existence proof that it wasn't insane to start down this road, and then we can optimize from there.